Hello and welcome back to our channel and to the ConQuiz number 12. As you know, we call it Concept Booster, and this is the last episode on thermodynamics, and today we will be discussing the part 4 of thermodynamics, Concept Booster MCQ, multiple choice questions. Okay, for your convenience, let me declare at the beginning that in today's questions, most of the questions I have classified in a few categories, and of each category there are a number of questions, and I have explained only one of them, and rest of the questions are of very similar type are given as exercise. Of course, the answer is given, but I am not discussing it in details. Okay, most of the questions are given left for you as exercise. Okay, so you can give pause, note it, and try to answer, and then have a match with my answers. Okay, so let us start the MCQ concept booster on thermodynamics. The basic preliminaries. First of all, which of the cyclic integrals must vanish for a closed system with PV work only? So there are four integrals are given, and the options are A, B, C, D, 1 and 3, 2 and 4, 3 and 4, and 1 and 2. So if you look closely, then of course you will find the answer to be C, and C means 3 and 4. So more than one answers, 3 and 4. So you see this is a cyclic integral over V, and the function is V itself, so it must be vanishing. And 4, Q reversible by T, so it is ds, entropy is a state function, so over a cycle ds over a cycle must be 0. So the other two of course they are not vanishing. Okay, so the next question, as I told you that will be left for you as an exercise, but the answer is okay, out of 4 options the option is B. You can easily check your argument. Okay, so the next question, which of the following pairs represents infinitesimally small quantity? Infinitesimally small quantity. So options are A, B, C, D, and the answers is going to be B. B means 2 and 4. You see 2 and 4. So dW reversible is minus PdV, and the fourth option is VdP. So they are of course in differential form, but the other two are not in differential form. It's a partial derivative, it's a given quantity, and delta V is a definite finite amount, not an infinitesimal quantity. Okay, so that's the clear answer. Now let us go back to equilibrium. Okay, this is a very instructive and demonstrative problem, and sometimes it defies this kind of questions or common sense. For example, we have considered a two-way reversible B. It's an equilibrium, so the Kx is mole fraction of B by XA square, right? This is Kx, and Kp, the partial pressure Pb and Pa square. But as you know from Dalton's law, Pb is mole fraction into total pressure P. So Pa square is XAP square. So if you separate XB and XA square, that would give you XB by XA square, and P and 1 by P square, so gives you 1 by P. But this yellow colored XB by XA square is nothing but Kx. So we get Kp is equal to Kx by P. So apparently it seems that Kp, it contains right hand side P. So Kp should be pressure dependent. Of course, we are considering an ideal gas system. Okay, but we know that Kp is not a function of pressure. So what is the fallacy? How would you explain? Actually, in this kind of expression where right hand side contains P, it may mean that Kp depends on P, or it may mean also that Kp on other reason, Kp is independent of P. So even if P is there, so it automatically adjusts Kx so that the right hand side remains the same to keep Kp constant. So here basically the answer is Kp is really pressure independent for this ideal gas system. Now the reasons on of the options is correct. P is 1 atmosphere, P0 is 1 atmosphere, delta G is 0 not equal to function of pressure, and delta G not equal to function of pressure. So we know that delta G is a function of pressure. And of course, P0 is 1 atmosphere and P is 1 atmosphere have nothing to do with this equilibrium problem. So only option is delta G not equal to function of pressure. And that is true. That delta G is minus RTL in Kp. So it's a logarithmic function. So naturally Kp would be pressure independent, and delta G naught itself is not a function of pressure. Okay. So that's why. So if P changes, Kx changes accordingly to keep Kp constant at temperature T, right? So C is the right answer. Delta G naught is not a function of pressure. That's why. Okay. And that's why in such a reaction, if we increase the pressure, so the denominator will increase, so that Kx would also increase to keep Kp constant. That means the more and more product will be obtained, as we can predict it from Lassatelier's principle as well. Okay. Next question. Which of the following is true in a reversible adiabatic expansion of a perfect gas? So we have to follow reversible adiabatic expansion and of a perfect gas. So IUPAC is followed for sign convention of Q and W. So if you look it carefully, that reversible and adiabatic, so Q is 0 and expansion, so work is done by the system, so W is less than 0. Now that option is available at B and D both, not A and C. So either B and or D is correct answer. But since Q is 0, so it does its work at the cost of what? At the cost of its own internal energy or enthalpy. So that must decrease. So delta U less than 0. So option D is the only right option. Okay. So option D is the right option. And now a series of problems I would leave as exercise, similar type problems. This is for reversible isothermal. The earlier one was an adiabatic. This is an isothermal expansion, again by a perfect gas. So try to apply your logic and try to find the answer, and answer comes to be A. Okay. The next question, again it's an exercise, and this time it's an adiabatic expansion of a perfect gas but into a vacuum. So of course it's not a reversible one, and again you can check your argument. The answer is B. Next one, which of the following is true in an adiabatic expansion of a non-ideal gas into vacuum? So the earlier one was ideal gas, and this time it is non-ideal but against vacuum and adiabatic. So again you can apply your logic, take it as an exercise. It's an interesting exercise, and you can find the answer. You will be happy that if you can match your answer, the answer is going to be C. Which of the following is true in a reversible heating of a perfect gas at constant pressure? So again this is given as exercise, and you can check the answer to be A. So if you're really interested to solve this kind of problems, you have to bear with me. You have to give pause at certain instances of the video and note the question and try to find the answers. Okay, that would be good if you interact with at a group. Okay, group of students or group of friends. Okay, the next question, which of the following is true in a reversible cooling of a perfect gas at constant volume? So it was heating and now this time it is cooling. So similar argument, line of thinking, and you could find the answer to be C. Next question, which of the following is true in Joule-Thomson experiment, adiabatic throttling by ideal gas? So in one of my earlier videos, actually I have explained the answers with a slide. So please I refer to go back to that video. Link would be there in the description, and the answer actually all are 0, and the answer is B. Q0, W0, delta H0 and delta U0. The line of thinking or logic that you can get from the earlier video. Okay. And next question, which of the following is true in a reversible melting of ice at 1 atmosphere and 0 degree centigrade? So at normal boiling point, 1 atmosphere and 0 degree centigrade, so it's a reversible melting. But if it melts, then it absorbs heat, right? So if it absorbs heat, then what about deltas of the system and deltas of the universe? This is the question. Okay. So this is first time related to entropy change. Earlier it was on Q, delta U, delta H and W, and this time is delta S and delta S universe. So the answer is A, because Q reversible greater than 0, it melts, so it absorbs some heat, right? And it's reversible, so Q by T delta S, that is greater than 0. And what about delta S universe? Because it's a reversible process, so second law tells you that the total entropy, that means entropy change of universe, that must be 0, because it's a reversible change. So the option A, delta S universe is 0 and delta S system is greater than 0, right? I think you have got my point. Which of the following is true in a reversible adiabatic expansion of a perfect gas? So again, same kind of question, and you can follow the logic, take it as an exercise. Answer is D, reversible adiabatic expansion of a perfect gas. Okay. Next question, which of the following is true in a reversible isothermal expansion of a perfect gas? So very similar question, only slightly change is something is there, and you can follow the argument on your own, though I have supplied the logic, but as given as exercise. Okay, so please apply yourself and I am sure that you will get it. Which of the following is true in an adiabatic expansion of a perfect gas into a vacuum? So this is Joule experiment, right? And in Joule experiment, as you know, that it's an isolated system, and there is no it's against vacuum, so W is 0 and Q is also 0 because there is no temperature change observed. So the isolated system Q is 0, but isolated, if it is irreversible process, then by second law delta S must be greater than 0. System or surrounding taken together, because it's an isolated system. Okay, so delta S universe, what happens to it? It's again greater than 0 for irreversible, and delta S equal to 0 for reversible. But this is an irreversible case, so delta S universe greater than 0. Okay, so the option is B, both are greater than 0. Okay. Which of the following is true in Joule-Thomson experiment, adiabatic throttling by ideal gas? This is on entropy change, but you can follow the same logic. Logic is supplied also here. Irreversible adiabatic, but delta T equal to 0, ideal, right? So you can easily see that ln V2 by V1, V2 greater than V1 is because it is expansion. So delta S greater than 0 from straight from the formula, and delta S universe greater than 0 because for irreversible change is happening here. Okay, that's all. Which of the following is true in an adiabatic expansion of a non-ideal gas into vacuum? So again, similar pattern, and please follow its logic, which is already supplied. I am not wasting my time because you can follow it on your own. Which of the following is true for the first step of a Carnot cycle? So there are 4 steps, as you know, in a Carnot reversible cycle. The first step, which one is true? So as you know that the first step is isothermal process and it does expand. So work is done by the system. So W must be less than 0. That means either B or D, right? But Q less than 0 or greater than 0. Because delta U is 0, CBDT, isothermal process. So it does its work at the cost of heat. So it must absorb some heat at the first step. So Q greater than 0. So out of B and D, D is the right answer. Okay. So D is the right answer. Now you can follow the same logic for the other 3 steps for all these 4 quantity Q, W and delta U and delta S. So please follow. The answers are given and I am not explaining. This is the second step. Answer is A. Exercise. Another exercise. This is C. The third step, also an exercise, and this is the 4th step, again exercise. The answer is B. So we can check the answers, and if you get some wrong answer from my side, please make comments in the YouTube comment section. Okay. Next question, the coefficient of performance of Carnot refrigerator. So we know that Carnot cycle engine, Carnot refrigerator and Carnot heat pump, slightly different expressions are there. So for a refrigerator, actually one of this is correct answer, and this is a bit informative question. The answer is A. Tc by Th minus Tc. Okay, Qc by W. So this is for refrigerator, Carnot refrigerator. And performance coefficient of a Carnot heat pump. So this is minus QH by W. Okay, and then epsilon is, which one is true? The answer is actually C, but that would be visible in the next slide, that why epsilon must be greater than 1, because the expression minus QH by W and the expression is actually, the answer is B, that is TH by TH minus TC. So TH is greater than TC, right? So the denominator is less than the numerator. So of course the result is greater than 1. So epsilon is greater than 1 always because of this expression. Okay. So thanks for watching. Our next video is much awaited quantum. So that will be session 13 coming soon, and we'll start quantum part 1 as usual with true false questions from quantum. Maybe more than one videos would be there because so many interesting true false questions can be framed from quantum conceptual background. So please bear with me, follow the notification, and till then please keep on watching, do subscribe and encourage your friends to subscribe. So thank you once again for watching this video. Thank you.